the second presentation about our course, which is on the future electricity grid. Don't know if... Oh, yes, it's gone. Thanks, Fernando. So, part 2 of this presentation. As you can see, I have 85 slides, which is a lot, so I will have to hurry a little bit. But don't worry, most of them are just with extra arrows on it. For those who weren't there last time, my name is Dirk van Echtem. I'm from Belgium originally. I got my first master degree from the Katholieke Hogeschool Kempen-Geel, and afterwards I did another master's in the KU Leuven, Belgium. I subsequently did a PhD in Belgium, and now I'm a postdoc at KTH, or the Royal Institute of Technology in Stockholm, Sweden. In the first part, we talked about the new situation which is there in the power system. It was dealt with the liberalization of the electricity market, how we experience new, smaller and variable energy sources, and what was the effect on the system in Europe. We also mentioned something about the investments in the transmission system and why they are lacking. In this part, we will talk more about the coordination in the power system. This will be a rather short part, and how this is evolving. I will mention Coreso, which is new for most people, I guess, in detail. And the two main parts of this presentation will be on power flow controllers and how they are coordinated, especially in a meshed power system such as that of Europe, and the supergrid, which is very popular. Well, it's not about the grid of 2050, maybe how we get there. We focus on Europe, but most of the things I think will be applicable for other regions as well. Not about smart grids, and I focus on transmission systems and not the distribution. The slides are from a grid operator point of view. So this is how we'll start. So we'll start with the introduction that we just did, and we'll now have this coordination in the power system. This is a bit of a repeat of last time. Before, we had vertically integrated companies. The generator company and the grid operator were one company, so the operator, the power system operator, he controls the entire power system. Unit dispatch is done by system operators. Topology can be changed. Reactive power is fully available for the operator. He can switch capacitors, but he can also change the settings, the voltage regulation, the VAR control of the generators. In extreme cases, international or zonal redispatch was done, and of course there was a cost for that. At that time, all generation was centrally controlled. Now we have more partners. We have this unbundling that we had, so we have different generator, transmission and distribution companies. We have the suppliers, we have power exchanges, renewables, and part of the results of that is that generation is no longer directly controlled by transmission system operators. The operators still have the same possibility. They can do unit dispatch if they want, but now they have to pay for that, and it's not very cheap. Topology changes are still possible. Reactive power, yes, capacitor switching, but they don't have the same possibilities with the generators. Sometimes they do, depending on the national regulations. And international and zonal redispatch is also still possible. What we did see is a significant increase of power flow controlling devices in the power system. This part will be treated. The significant increase of power flow controlling devices will be discussed with in more detail later on. Another part in the system is that we have less stable pattern due to the market and due to the We also need to have a more firm capacity in the market. So in total, it means we need for more control and we have less free means. Different systems are interconnected. It's once there are different synchronous zones, and all these small zones, the synchronous zones consist of different control zones, and each of them is operated independently because it's an own company. However, we have an international market operation, so we have transfers and we have security measures that are done internationally. And if you operate your power system, you also affect the system, your neighboring systems. The information that is currently exchanged between operators is the grid status, so what lines are in service, what aren't, the day ahead congestion forecasts, the expected available capacities on the border, and any emergency that's happening. So if something is happening, they will communicate this to the neighbors, because this might result in undesired effects. When doing this exchange, not everything is exchanged. There's a limit to that. Usually only aggregated data is given, and the grid data is provided on a need-to-know basis. This is for several reasons. It's not very important to give 30 kilovolt system data to a neighboring TSO. He has no use for that, so you have to make sure that only the useful information is provided. And also there's a possible problem for competition problems. All in all, it's a quite well-working system. One slide about the day ahead congestion forecasts, so you can see how this principle is done. So they start with the estimated zonal grid of the day ahead, and they take their power system and they cut it at the borders, where they just cut the international cross-border lines in two, together with the expected aggregated load and generation patterns that are expected for the next day. So they have bits, and they will bring this in the system. They can have the state of the devices that are in the system, and if you take all this into account, you can calculate the flows in the system as you expect them to be. At the borders for the international trade, you just put injections in the different interconnections. You guess what the reactive power is, and then if you have all this data, you send it up to a central computer where the merged system, so if you have all the different grids puzzled together, they calculate it, and then they see whether there is a problem. If there's no problem, it's okay. If there is a problem, then TSOs have to negotiate what they will do to alleviate these problems. And this can then be international redispatch, or opening a line or closing a line, or something similar. As mentioned, it works quite well, but still there are some problems. Although we have this forecast, we still have unexpected loop flows. We had a slide of that last time, a few slides. We also have this uncertainty in the system. It's quite high, and even if we have this communication, we don't seem to reduce that. Furthermore, we have blackouts or near blackouts due to the lack of coordination or communication that we have. You probably remember, or if you've heard of, the Italian blackout. At that moment, it could have been helped by simply stopping the pumped hydro, or reverse it so that it would deliver energy instead of taking energy from the system. And it might have helped the system. One of the main problems there was miscommunication. The November 2006 event, where UCD almost had a blackout, again, communication between operators failed. Opened the line 4 hours before they originally intended, and they forgot to mention this to the neighboring TSO. Of course, the situation was not as they expected, and a sequence of events happened which could have been avoided were there better coordination at that point. of course, there are limitations in how far you can cooperate. There are always unforeseen events, so the cooperation will not make you lose all possible. Well, the need for having a security margin. Not everything is known, but with the higher uncertainties and less control options that there are there now, the system operator has limited tools to play with something if something happens. Some problems might be easily solved in another zone, while they are difficult or expensive to solve in your own zone. Another problem is that system-wide security assessments, so cross-border security problems, they are not updated or performed during the day, or not sufficiently. And as a solution for that, or a first step towards this solution, the Belgian and French TSO ELIA and RTE started with a company called Corezo. This company was founded in 2008, in operation since last year, about a year ago. By now also National Grid has joined it. And the idea is that they provide a service, like a security service, which is cross-border for every TSO which is a participant in that. So what do? They deliver this service, so they proactively try to assess the safety level of the complete network of the different TSOs, day ahead and also in real time. They have no operator rights themselves, but they propose to the TSO the implementation of of an optimized coordination actions to limit the risks that are there. They relay the information, so they don't do anything themselves. I repeat that, but they calculate what the system is, and then they propose and give the information to the different operators. Also, ex-post analysis and review of what the operating procedures are or the events are is part of their job, and they provide a D-2 capacity forecast. Their focus is on the international grid, so the cross-border interactions and the integration of the renewable energy sources. As I understood, now there are only 3 TSOs member of it, but I understood that many more TSOs, that more TSOs are invited to join them, and their goal is to have a good coordination center for entire CWE, which is basically the Benelux, France and Germany, so that every TSO in that region would provide this data towards this Corezo, and that they could improve system security over there. The second, more elaborate part of this presentation deals with power flow controllers, and I will focus on the coordination of these devices. I will not go into detail about the techniques part of this, but I will talk about the power flow controllers, how they are used in an international context. I will have a small example. The need for coordination will be addressed, and I will try to give some insights on how we could do this. So what is power flow control? Well, sometimes it's explained as bending the laws of Kirchhoff. If you have a normal system, the power flows according to laws of Kirchhoff. You've seen this when you were in secondary school, I guess. So the law of lowest resistance. In a mesh network, the relative impedance of the lines determines how the power flows are. When you use power flow controlling devices, you can influence these power flows throughout your system. Simplified, they work just as a valve does. And as a result, you can relieve the tension on, or not the tension, but the stress on overloaded lines, and you can adjust the system according to the situation that you want. You might want to have a different operation day or night, summer or winter, or import or export, and in some maintenance situations you might have a different system operation. How does it work technically? Again, I will not go too much into detail, but the very basic equation for the power flow, which is going through a simple transmission line, is written there. It's the active power flow is the product of the amplitude of the voltages at sending and receiving ends divided by the impedance and multiplied by the sine of the angle between the two voltages of sending and receiving side. So below the very simple network, and on the right hand side there is the phasor diagram. So what can we change? I see here some comments that someone doesn't seem to see the presentation. I hope this is not a general problem. And in case I will continue, please interrupt me in case there should be a major problem there.
Yeah, you can go ahead, Dirk. At my side, I can see that. So I hope this is not a general issue. Okay, so if people can confirm, okay, you are doing. Most of them are okay. So we are setting a new version of the webinar platform. So probably because of okay, most of them are okay. So you can go ahead. Thank you, Dirk.
For those that don't see it, the presentation is also available for download, so maybe you can open it in a PDF viewer next to it. Okay, I will just continue then. So what can we do with our power flow equation? As you can see, we can change the voltage at the end sides. Of course, only limited availability or possibilities there, because the voltage still needs to be between plus or minus 5 or maybe 10%, but you cannot play too much with that. The second thing that we can play with is the impedance of the line. The impedance itself, of course, cannot be changed, but you can change the total impedance by adding a reactor or a capacitor. You can alter the impedance of a line. And lastly, we can change the angle between voltage and the two voltage ends. Different technologies exist, and usually, well, you can have a mechanically switched, thyristor-based switched, or very fast switches such as IGBTs. The power flow controlling devices are a subset of what people sometimes mention as FACTS, or flexible AC transmission systems. Some examples: a phase shifting transformer, which is a mechanically switched device. So it's basically just a transformer, or sometimes two transformers, and the basic principle of how it works: it injects a part of the line voltage if you have here the phasor voltage here of phase 1, you inject a perpendicular voltage like this line voltage, and you inject a part of that, or transform part of that, in series, and you will see that the effect will be that you push the voltage between sending and receiving side from each other. There are different types. Most important is that it's relatively cheap, robust, efficient, and slow. But it is used quite often in if you only need a steady state system. Another example is a thyristor switched or thyristor controlled series capacitor. Basically, this is a series device, a capacitor, and you can change the size of this capacitor, and that makes that you can compensate the natural series inductance of the transmission line, and it's especially used for longer lines. It's also possible to use the dynamically because it's quite fast to operate it. Well, I wouldn't say more important, but this is a technology which is more used, I think, is the high voltage direct current. Its main used component is the line commutated Hvdc, which is existing for over 50 years. It has high ratings. It's relative low losses, about 0.8% per converter, and it has as a disadvantage a strong AC grid to connect to. And here you can see a basic converter setup where you need the AC filters on the left hand side, and then you have a 12 pulse converter for a thyristor bridge which connects to a DC line. The AC grid to connect to, you need that because the thyristors cannot make their own 50 Hz or 60 Hz signal by itself, and they need to have a commutation. The VSC, the voltage source converter HVDC, is an alternative which is relatively new. It's about 10 years old. It uses fast switching, so IGBTs, and the result is a PWM signal. Basically, it's a big frequency converter. As you can see, the waveforms here are the more harmonics, the more switching. They have higher losses. The harmonics all are very high harmonics, so it is easy to filter, and the result is that the total grid makes it a very easy to use, relatively small because small filters installation, which has its own rotating field, so you can even feed into an island, or for instance an offshore wind farm. A disadvantage is that there are currently only two manufacturers, ABB and Siemens, which both have a different setup. The scheme that you see here is the ABB scheme. The Siemens scheme looks different, but the result is about the same. And in voltage then in the end, and in operations. Areva is said to be developing a device similar to this also, but I didn't see a result of that. Just want to mention that HVDC is a special power flow controller. It allows full and independent active power flow control. So if you have a phase shifting transformer or a TCSC device, then the flow to this line, to the line where this device is placed in, is dependent on the rest of the system. You can control it, of course, but it's not very it's still dependent on the entire system power flows, while the DC system cuts the system in two parts and makes the power flow control fully controllable. The VSC HVDC also allows independent reactive power flow control at both ends. As such, I think the HVDC line is an ultimate power flow controller, but maybe not a very true power flow controller. Just to see it as an example, if you have two systems with only one HVDC line in between, then it's not really a power flow controlling device, because the device can only take care of the imbalance between the two. If this would have been a phase shifter, the situation would be slightly different. If you have a parallel line, of course, you can have a full power flow control. Everything which is not going through the DC line will go to the AC line. So then it's what you would expect to happen with a normal power flow controlling device. And if you have two devices, or all the links between two systems are DC lines, then you do have a full coordination needed if you want to have power flow control, or even a stable operation. I will not go into detail in this picture. This is just a classification of the different devices that can be used as effects. You have the shunt devices, series devices, and combined devices, and then in vertically you can see the different technologies, so the conventional switch, the mechanical switch devices, or the fast devices such as thyristor valves and IGBTs. So why so much time spending on these power flow controlling devices? What you see on the left hand side is the Benelux, within the north the Netherlands and below Belgium, and a very small part of France and Germany. For those who are not very aware of the system size here, I would say that the north to south axis is about 500 kilometers, and the left-right direction is about 400 kilometers roughly. So that means it is a pretty small system, and there are quite some power flow controlling devices in. There is a HVDC connection between the UK and France on the left hand side. In the upper north there are two phase shifters in the same line placed in Maiden in the Netherlands. Gronau, Germany, just below that there has another phase shifter. And then there are 4 in Belgium. As you can see, the 3 north, the Zandvliet and Van Eyck phase shifters are placed on the interconnections with the Netherlands, and they control the complete power flow through the going from the Netherlands to Belgium. And then there are plans for more. BritNet will be built, and probably in 2011 they will finish it. There are more plans for a line between Belgium and the UK, and possibly even Belgium and Germany. So more lines are coming up, and these are a high number of power flow controllers, and most of them have been built in the last 10 years. It's only the Gronau phase shifter and the HVDC line between the UK and France that are not that are older than 10 years. So how you control these devices? Well, last time we mentioned that the power flow controlling device is a nice investment for a transmission system operator, because it can be a local investment and you can extend the use of the system, or you can extend your grid for a while. So if you invest in that, you will also control the device, and you will control it to your own objectives. And as it is paid by the local market participants, even your regulator will say that the revenues should be returned to the local market as well. And that means that you will use your power flow controlling device, such as your phase shifter, to optimally use your transmission system, whatever this optimally means. It can mean minimum losses, maximum security, maximum transmission capacity, or usually a combination of those above. However, although you are installing these devices in your own system, they have effects that are not local. As you could see from from the picture before, the devices are mostly placed on the border, and the effects are so that they reach far into the neighboring systems. Most of the devices are even intended to influence external powers. For instance, the power flow controlling devices in Belgium, they limit the flow that goes from the north of Germany to the south of Germany, where loop flows were happening because of the increased generation of wind. A few smaller pictures to show you the problem. Let's say in the first case we have a very simple system with 4 zones, where in the south, in zone C, there is a generation, and in zone A in the north there is a load, and zones B and zones D are just transport zones, transfer zones. Let's assume that both of them have 50% of the flow through their system. In case zone B decides to build a power flow controlling device, he can shift the power, let's say, from 20% to 20-80% instead of 50-50. And in the third picture, you can even assume that he goes to minus 110%. This seems to be unreasonable, but on the other hand, maybe this minus 10% what was decided on the day before in the capacity planning, and the settings were set, and some event made it completely different. Of course, you can see this is not optimal for the system at all. In the last, in picture D, it's even worse, because their zone D also invests in a power flow controlling device, and he cancels the operation. So 2 companies or 2 TSOs have invested in an expensive device which is not very useful. As an example, I will just mention the different losses in the system with different zones. First of all, higher losses in one line is not the same for higher system losses. As a very simple example, the little scheme that you see there, where you have 0.1 per unit resistance and 0.1 per unit inductance in parallel, the losses, I've written the equation there, and of course it's only the current in the through the resistor that causes losses. So if you shift power to the line with the highest X, you will have, instead of the line with the high R, then you will have lower losses. But in most transmission systems, the X/R ratio is more or less constant, and then if you use a power flow controlling device, the overall losses usually will increase. But as mentioned before, it's not very important for most TSOs because they don't look at the system losses, but they look at their own system for their losses. Just a very small system to show it. The 39 bus system, you can download the IEEE 39 bus system and do this small test yourself. I placed a phase shifter in the green lines between those 2x2 nodes, and I tried to check what the losses were in the system. Okay, so this is the contour plot of the losses in the three systems. So these are some kind of bowl-shaped surfaces where we have three minimum losses, three best points for zone 1, zone 2 and zone 3, and of course these three zones are not the same. You have the three different optima. Let us say that the first power flow controlling device is operated by zone 2 and it will be operated in somewhere its lowest point. So let's say that in that area is somewhere where zone 2 wants to have its operation. And if we then look at the second PST, which is controlled by zone 1 or zone 3, let's say zone 1 in this case, it will be operated in the indicated area there. And as a result, we can see that the operation area is actually not good for zone 2, which invested in a phase shifter. So it's some kind of suboptimal optimization. We have three zones, three optimal phase shifter angle settings, and there is no coordination between them. And what is good for one operator is not necessarily good for the other one. There could be some kind of Nash equilibrium, so that there is some kind of competition that people go to, like a suboptimum based on the settings of the other ones. But most important is that the best for the system is not achieved. I have some numbers here in the table below where you can see that the best solution, which is the last column, is not one of the ones before. And sometimes there can be quite some difference, so I will not go into detail. I think it speaks for itself if you want to go to that into detail. So why is there a need for coordination? Well, of course there are different objectives. You want to you minimize your losses, not of that of your neighbor. You want to export, you maximize the export to B and not necessarily import from C. And of course objectives can be including, but it's good for you for zone A is not necessarily good for the other one, and the other way around. And as a general conclusion, we can maybe say that the global objective is generally not reached when there are multiple objectives. And as such, TSOs are not competitors. They don't fight to have the best one. They are not fighting against each other, but each is just doing his own operation of the system. And rather unwillingly, they are obstructing the other TSOs and using the system at their best. It's also clear that if you change the losses, if you change the transmission capacities, that it has an influence on the financial issue, financial side. And if you want to do this coordination, you have to communicate, of course. So how can this be coordinated within Europe? First of all, traditionally most power flow controlling devices were set for a local single control objective. They were there because one line was overloaded and there's just a local problem. and in that case you don't need a specific coordination. Another possible way to coordinate would be no coordination at all and everyone does what he wants. This was maybe the example of the losses that I had before. Everyone does his local objective and let's see what happened. And the only coordination that is done is for safety. This is actually more or less the operation that is at this moment done. One step beyond would be uncoordinated operation. With this I mean you optimize, but you look at your neighbors and you know that they are optimizing their system as well. You would go to some kind of a Nash equilibrium where you have some kind of gaming against each other. It might have been better if you would include the power flow controlling devices and to coordinate them in a market environment. As I mentioned, power flow control is money, so why not? As a very small example, this graph below, what is it? I had a very small system and I placed one power flow controlling device phase shifter in that system and I changed its angle between -25 and 25 and I calculated the system losses. You can see the blue line for zone 1, the red line for zone 2 and the green line for the complete system. As you can see, the complete system has a minimum loss around 0 and zone 2 has its minimum loss around -6. You can see that there is a difference in losses, so that means a difference in system operating cost between zone 1 and zone 2, and maybe zone 1 is willing to pay zone 2 to move its phase shifter angle towards 0, and this would provide a certain amount of money to compensate for the extra losses for zone 2, so there might be something in it for both of them. Regional coordination. I mentioned last time that there is a new setup of the EU, which is this regional initiatives, for instance CWE and other zones. Why is this a good idea? Because although they influence the neighboring systems, power flow controlling devices don't influence that far. The phase shifters in Belgium do not influence the power system operation in Poland that much. And this is also something that is now currently available. There is a current framework. It might be a good step to do it there. And as such, Coreso, which I mentioned before, is taking the first step together with, for instance, the University of Leuven. Excuse me. A next step might be to do it in the full system coordination. This optimize the entire system to a social welfare, and it would for the better internal European energy market. And this can be done, for instance, by a new organization, a phase shifter coordination group or something like that. But the problem is that they probably will not have enough power to say anything. The European Union seems to be happy about the topic of an independent system operator, which is that you have a grid owner separated from the guy or the institution that operates the system. The question there is who will invest and to what objective will you then optimize your system. So this seems to be quite difficult. And one single European TSO is maybe the best idea of them all, but then that means that the national assets of the different transmission system owners from different countries will have to be merged into one. And this is something that may not happen in the near future in Europe. But in the long run, that might be the best solution. As a first step, I would say that regional coordination is the way to go. One slide about the regulatory framework. At this moment, power flow controlling devices are just not mentioned, although that they do have a strong influence on neighboring systems. For instance, the UCT Operation Handbook, which is now into NSOA, mentions BSDs as a possible means of guaranteeing security, but not more than that. So there is no special required agreements. I would say that the first thing that there would be the first thing is that there is a need for more communication between TSOs, at least tell what is the current situation and how you're going to operate your system. In a future European regulation, I would say that power flow controlling devices are needed, do need some regulations. So we are now at the current state. We have a first step into a further integration, but we're not there yet. Okay, the final part, I'm slightly behind schedule, deals with the supergrid. Why do I find this important? This is because there are many occasions where you have a lot of people talking about the supergrid, and they talk about this is the solution for the integration of renewable energies and the way to go in the European system. And I have to agree, if you would have a supergrid, this is indeed a very good step towards decarbonization of the society, and it would be a very good solution. However, there are still some problems, and I would like to try to address these problems, or at least tell some current outstanding issues. First of all, what's a supergrid? Well, for me, and I may use a popular definition here, a supergrid is an overlay grid connecting different generation and load centers over larger distances. And as such, it serves as a backbone. It adds reliability, security of supply to the system, and it offers redundancy. Some people also call it hypergrid, or maybe even something else. Now the question is it new? Well, in fact it's not. It's a recurring issue. Let's say 120 years ago, the electricity transmission started from one generator to several local loads a few hundred meters away, and then you had generators connecting to each other, so there was larger distances, and then the grids became interconnected and increasingly higher voltages. As an example, we can have the 400 kV grid, which is the supergrid if you look at it in terms of the 1940s or 1950s. This is a picture that I borrowed from someone showing the ideas of a supergrid right after World War II. And you can see here that the idea is that you have three lines more or less in parallel: a north schiene, which is a line, Dampf schiene, which is a steam line, and a south line, and they would then be interconnected by some kind of a meshing system. And this is, in fact, they implemented this. It doesn't look exactly the same, but basic idea is there, that they would have 400 kV on every point and on every line, and connecting them. So this is a supergrid of the 50s. Why do we need a new one? Why do we need an overlay one? Well, first of all, we want to connect all these remote renewable energy sources, and there is plenty of renewable energy available. If you see what the influx is of solar energy in the world, we only use a very, very small amount of that. Especially for electric energy, it's almost nothing. So if we would have solar energy from the Sahara, and you can see here the picture how big the surface would be. The world is the top one, the biggest square in the Sahara, the red square. This is how much surface full of solar panels you would need for providing the world with electricity. So if you would bring that energy from the Sahara to Europe, and maybe from the wind areas, I'll show you the next slide, also the North Sea, you will bring those together to Europe. We have plenty of renewable energy available, but we need to connect them. The grid is not there, so we want to have this extra power. Also, we possibly need the hydropower of Norway and other regions to balance our system. For wind, I made a very small calculations. I did it with installed capacity and not with energy provided, so it's maybe not very perfect, but at least it gives an idea about how big this, how much surface we would need for Europe. If we would say that we would have about 1 kilometer between two windmills, and that we would have in the future 10 megawatt per windmill, and we count for 600 gigawatt of generation UCTE, the capacity factor taking into account, then we would have roughly, to provide enough energy for UCTE, about 180,000 square kilometers, or meaning a square of 430 times 430 kilometers, or maybe a 100 kilometer wide, 1800 kilometer long coastal track. Yes, this is a big surface, but on the other hand, Germany has about 2,300 kilometers of coastline. So if you combine a part of that in Germany and a part of that around the UK, around Scotland, and maybe a part of that around Spain, we might just get there without too much problems. Many people have proposed a supergrid. Even Greenpeace and environmental organizations, they have different outlooks. Yet we're not building one yet. What do we need for technology for the supergrid? First of all, we need high power transfer capabilities, and this for long distances. The efficiency should be as high as possible. Of course, it should be cheap. It should allow offshore connections, because we intend to have a lot of power coming from the sea, or at least from across the Mediterranean. The reliability should be as high as possible, and of course it should work with the thing that we have now. This is partly a repetition of last time, a repeat of last time. So we have the different technologies that we can use. We have the overhead lines, which is of course not possible if you want to have an offshore line. AC cables are limited in length and rating. LCC HVDC seems to be a problem if you want to connect offshore wind, because it cannot form its own rotating electric field. And VSC HVDC is usually seen as the most appropriate if you want to have an offshore system. But it has high losses, and the capacity at this moment is also quite limited. As a result, at this moment we don't have anything which would be perfect. VSC HVDC for an offshore grid, yes, but it needs some development. AC overhead line, well, if you can put it somewhere, yes, but maybe that's not something that is useful for Europe. So I think, in my opinion, the VSC HVDC system seems to be the most appropriate if there would ever be something called like a supergrid. Why? Well, we already have quite a strong AC system. It may need some backup or may some strengthening, but we could, yeah, as many load centers are located relatively close to the sea, we could connect to most of the areas quite successfully, I think. What is available? Well, how big should it be? First of all, it's not super if it's not bigger than what we have now, so it needs to be, yeah, bigger than what we have now with 400 kV AC, and the existing AC system would be roughly about 2 gigavolt ampere per circuit. That means that if we go for a bigger one, we should go to 5 gigawatt, 10 gigawatt maybe, and for that new developments are needed. At this moment we are not near that amount, especially not if we want to have cables. For cables we are limited to about 2 gigawatt at this moment. Another thing that we need to think about, and we need to think about it before we build it, is about standards. The AC system has standards. Everyone uses 400 kV, at least in Europe. There are different voltages used elsewhere, but you cannot connect different voltages, of course. Once chosen, it's difficult to change, because if you cannot integrate existing or maybe upcoming lines with that system if it's on a different voltage, of course. Another standard that's important is that different manufacturers must be able to connect to the same DC system. There shouldn't be any vendor lock-in. It's not it cannot be possible that only ABB or only Siemens delivers material for that. That would not be acceptable in the system. So if there is a Siemens converter at one hand and the ABB converter at the other hand, they should not influence each other. And the control system should be in a more or less similar way, without having any problems with the AC system. So how would the grid look like? And I'm not going into detail with where should it connect to in Europe, because this is a completely different question. So would it be enough to have a single line with different tappings as shown here, a multi-terminal without redundancy, or do we want to have redundancy in the system itself, or maybe partly? In this case, in the figure here, the AC and the DC system offer each other's redundancy. A complete different setup might be that we don't have a real DC grid, but we have a grid of point-to-point DC lines. Every line in the DC grid is a separate line with a converter at both ends, so basically it's exchanging the AC lines with the DC lines. This would allow full control, and another advantage would be that all the protection can be done at the AC side, which is much easier. However, you would need a lot of very expensive and very lossy converters, so maybe this is not the best way to go. The most advanced and most difficult situation if you have a meshed DC grid, where you have redundant lines, multiple connections, even DC connections without a node, and there are only converters placed at the interface between AC and DC grid. This system would have lower losses than the previous one, and it has redundancy. The DC flow cannot be directly controlled, only the interface between AC and DC, there the flow can be controlled. For the Seegreber group B452 on DC grids, this is the only real DC grid that they consider. And when you're connecting to this AC system at this moment, as we have it now, not a lot of points really can take 5 gigawatt in either direction. So only a few points are strong enough. That means that you need to reinforce the existing AC system as well. And this reinforcement might be even that you have a complete change in build-up. Originally, you put your grid from generator to load, and it's oriented like that. But now that we have this supergrid, or might have this supergrid, it will connect probably to the shore. That means that you will have to have your AC system brought to the shore. So that means that you will have a different build-up of the system. For instance, in North Germany, this would mean a complete different situation. Concerning security, we do need N-1 or an alternative way of security. Now, if we have a big terminal, 5, 10 gigawatt or something in between, and it is disconnected from the system, this will have a serious disturbance in the system. We might need to re-evaluate how we do our security analysis. And will we have 1 or 2 connections or so? Because if you have only one, this will have the complete different power flow situation in the AC system when changing or when losing one terminal. Another important question is how are we going to connect to the smaller synchronous zones? For instance, Ireland, which has only 7.8 gigawatt of installed capacity. What are we going to connect to there? And another smaller one with 61 gigawatt, which is maybe only 10 times the rating of a single terminal, Nordel, so this is Scandinavia. Maybe we should have different operations over there. Protection is often seen as one of the most difficult ways or most challenging tasks for the supergrid. Currently, if you think about the VSC HVDC system, the protection system as follows. They don't interrupt, if there is a fault on the DC system, they don't interrupt the DC current, but they open the protection systems on the AC system at both sides of the terminals, and thus also eliminating the fault current. So this is the easy way. of course, it's not sensible, it's not useful to disconnect the entire supergrid every time that there is a fault. So this cannot happen. It's not acceptable that this new form of transmission grid will fall out every now and then for maybe a few seconds to open up a line. Now, why is this important and troublesome? There are some supergrid protection boundaries. First of all, if a fault happens in a DC system, the current rises very rapidly in all transmission lines, all DC lines that are connected. However, we need to be selective. Only the affected DC line must be switched. Another disadvantage of the voltage source converter, or maybe even DC systems, is that it's power electronics and it cannot withstand very high overloads for a long time. So it has to be fast enough. And this, of course, with no inductance to limit the current at all. And of course, we only want to have the operation of the protection system in case that we actually have a fault, and not during any load change or an AC fault, or maybe a terminal that is disconnected, but not necessarily for a fault situation. So what are the consequences? So the fault location, the branch, must be detected within a few milliseconds. It's too fast to have communication between the measurement devices, and you need to have an independent detection system in every protection device. The opening should be done at both sides of the faulted line, and there is no opening of any other branches, of course. Only the ones that are affected should open up. And if this is not working, of course you need to have a backup somewhere. For this you need super fast DC breakers, which don't exist at this moment. So and this super fast DC breakers are needed because if you wait longer, you'll burn up your IGBTs. I will just show very quickly, because I see that I'm running out of time, how the protection is done. Let's consider this 4-terminal DC system where somewhere a fault is happening. This fault will cause all the currents to go to that point, and you will have a big overload, and of course you want to isolate this problem. What happens is that the protection system needs to determine, okay, it's this line that's actually challenged, and this done by measurements locally there without communication, and then the transmission line should be opened, the correct one. This all within, let's say, 5 milliseconds. The power balance, this is another problem. This is probably less challenging than the former ones. At any moment the power balance must be zero, so you need to have a zero, you cannot store energy in your DC lines, and you have the injections must be fully controlled, but there is some compensation for losses. So you will have some kind of a slack bus or distributed slack bus operating in your DC line as well. The flows in the DC system are according to Kirchhoff. So it could be that in certain situations that you have an overflow in some of the DC lines. As mentioned earlier, so the DC system will have a profound influence on the AC system flows, and also changing power injections between nodes can have an important injection. For instance, if you decide, because of the market decides that the injection should not be in Denmark but should be in Italy, because they pay more at that moment to have this power injected there, this will have a large influence throughout the system. How this interaction will or should be done is not very trivial, especially if you have this multiple zone and multiple synchronous zones working. Furthermore, an HVDC system is very dynamic, so first of all it should not jeopardize the AC system. It should not have any bad interactions with the AC or DC controls. Secondly, if you have two close by terminals, they might interfere. However, a good thing about this very dynamic operation is that you actually might use it to increase the stability and damping in the system. Of course, this is not very simple, and extensive calculations might be needed, but there is a possibility for that. Another advantage, possible advantage of a supergrid might be that you segment the AC system. You cut it up in smaller parts. Instead of one big synchronous zone, you cut it up in very small parts, or smaller parts. As a result, AC power problems are not transmitted throughout the system, and they're limited to each smaller grid. As a result, also part of the synchronizing power would be lost. So it is some kind of an advantage disadvantage. It might be an option for systems which are currently already loosely or loosely connected or non-synchronized. Maybe, for instance, in the USA, I've seen a proposal for that. I'm not really convinced of this. From the economic point of view, why building a supergrid? There are 4 reasons, economic reasons. You access the remote energy resources, higher penetration of renewable energy sources by balancing, like this large-scale balancing. You improve the grid security, and you have less congestion, meaning higher profits in the system. However, it's an expensive installation, very expensive HVDC terminals, cables, and whatever. There are other resources. We don't need renewable energies. We can also use coal or whatever, or there can be an optimal generation mix, or maybe we have closer by renewable energy sources which might not be so efficient, but closer to the grid. And there might also be other cheaper solutions like radial AC links. So we have to check what is the best opportunity. And we might also just be happy with our AC system as it is, or maybe upgrade it slightly for the next year. So the most important question here is, what's the payback time? Is it interesting from an economic point of view to install a supergrid? And I'm afraid this is not an easy question to ask. So what about regulations and ownership? There are many operational questions that are still there. First of all, who will invest in the system? Will it be the TSOs or NSOE, the governments, the European Union, generator companies, or private investors? And whoever does the investment, they want to have a return on investment. So the operator or the owner, they will determine how the grid will look like, how many connections, to what point, which is the connection point, what will be the rating. How will the combined AC and DC system be operated? This is also related to who owns it. And how will you earn money? Will it be regulated or a merchant grid? Are there connection charges for offshore generators or not? Will there be a regulating authority, and who will it be? And what happens with the multi-zonal regulations? So it's not so easy. If you connect your terminal to a system, for instance, you connect the terminal to the Netherlands, what would be the interaction there between, let's say, Acer and the local regulator in the Netherlands? Okay, just the 2 conclusion slides. I'm well aware that I'm trespassing the time zone. The conclusions first on the coordination. It's not trivial to coordinate in a multi-zonal transmission system. We have a cooperation, we have a coordination, and it's working quite okay, but maybe it can be slightly better. There is a new initiative called CORESO, and this is for Belgium and France and the UK. Those TSO are currently involved, and I think it's very promising in this coordination aspect. The second part of the presentation was especially about the coordination with power flow controlling devices. They are more and more present in the power system, and you can change a lot of operational aspects with it, the losses, the transmission capacity, and the security. However, they don't only influence the local system, but also that of the neighbor. So this makes that the coordination is even more important. Different manners of coordination are possible, but at this moment I have to say that no real coordination exists. So we should start with more communication and then implement it in the regional initiatives framework, or maybe CORESO. The best thing would be full coordination, maybe with a single European TSO, but I don't think this is for the near future. And the current situation is not ideal for full implementation and of the internal European energy market or electricity market. the last part, I discussed the supergrid, and it's often seen as the ultimate solution to integrating renewable energy sources, and I have to say yes, if we can do it, probably we have an optimal solution. However, there are still some challenges. There are technical and operational and economic challenges that need to be resolved. Some of them might be easy, but some others still need some development. So I would say yes to a supergrid, but maybe not for tomorrow. And then I have one more slide. It's this one. So thank you for your attention. I hope it was interesting. And if there are any questions, I would take them now. Thank you.
Okay, Dirk, thank you very much for your comprehensive and interesting presentation. So we will go for a quick Q&A session. So let me one moment to find the question. So you can submit your questions. We see here that we have already some of them. So let's go one by one. So from Ankajan Barbu,
I am not sure
what about the new developments
in what aspect
in
that you
Nordic countries?
want me to answer this question, whether it's on the coordination, of which I'm unfortunately, although I now work in Scandinavia, in one of those Nordic countries, I'm not yet well aware about what is done here actually, because the Nordic countries operate their system different than UCT does. Also, there are maybe, I don't know which 9 Nordic countries that you mentioned, probably because there are different zones. For instance, there's the Baltiazo, which are working completely different compared to the Nordel region, and so I'm not quite sure what you mean with this question. I'm sorry.
Okay, so next questions in person. How do you see the role of the new European agency for the energy regulators in addressing some of these questions? Well, this is something
Acer, the new
previous questions from
Acer will have a strong position, because at this moment there is a big problem that there are too many, in my opinion, that there are too many regulators which all have their own agenda, which doesn't really help. And it's logical that they have their own agenda. I'm not saying that they do a wrong thing, because they work like any independent organization should do to optimize their own system. And I hope that the European Agency for Energy Regulators might streamline everything, but the question is how much power it will be given. Okay. I think it's not really the reactive power flow that you want to control in the system. The reactive power flow is
in a network.
You want to have the reactive power only available at the places that you need, and that means that you have to have them as voltage support. So it's not really, you don't really sell reactive power. The only thing is that you needed to have a good system operation. So in cases that having local reactive power if you have local reactive power problems, you want to have this solution. So then you use a STATCOM or a SVC device typically to boost up the voltage or to compensate for flicker in the system caused by, for instance, a wind farm.
Okay, very well. So next question, when is it, in slide 42, what's the expected balancing capacity as percentage of total generation capacity? So let's switch to slide 42. 1 second, please. Meanwhile, if
I'm not sure
already
that
have some
this
elements,
relates to slide 42,
yes,
but
here we are.
maybe if it's 42
So
in the
the floor is
bottom,
yours.
that could also be the case, because I use frame numbers with my LaTeX slides. So check.
Okay, so as the question
I
relates
think
to the
this
amount
is
of balancing
dependent on which
required,
sort of energy source that you want to
maybe you
balance,
have in mind any
or which
ratio.
system that you have. If you have a very dependent energy provision, which is always there and very certain and no chance of failure, then it will be very low. Of course, if you have a very unreliable energy source, or reliable or unpredictable, I would rather say, then you need more. So it is a very difficult to calculate this, and maybe or not, maybe not to calculate, you can calculate, but to say, put a number on it. And in the last presentation I mentioned that you should work with loss of load expectancy calculations to check what is the chance that you lose load at a certain point, and that at that moment you can decide to have more balancing capacity.
Okay, great. So sorry for the page numbers. I think that in the presentation it was indicated, but not at the right place. So I think there is some misunderstanding with this. In any case, I think your answer is still right. Okay, so we can go to other questions. So
I don't really understand this
next
question.
question, since the power is
Oh,
uncertain,
we had
how the
some
power station is
loopback.
connected to the grid? I'm not sure this we understand the question. Okay, so we can skip, and in the meanwhile we can ask
Well,
Ravindra
this
to
is
submit
a
again the
very, very
question, providing more
difficult
details.
question
Thank you.
depending on
So
many
from Virgil,
small
what
factors.
is
At
the
this moment,
horizon
I think
time
technically
for the
we're not
European
there.
supergrid?
However, if some developments happen which may not be that far away, and there is enough money to invest, and there is a need to invest in a supergrid, it's sensible to have a supergrid connecting all the regions and not having radial lines. I think the earliest would be 2020, but I would say that if we would have it in 2030 or 2040, that would be more accurate. That doesn't mean that we cannot have parts of what will be the supergrid in that time. When I showed you this picture of the 1950s situation with the 400 kV system, that absolutely was not something that was developed in one time. They didn't put the 400 kV grid from zero to completion in 1 year. That took 30-40 years, and it will be exactly the same with the supergrid in Europe. I mean, maybe they will start with a big power line between the north of Scotland and Germany, and then maybe they will connect one extra line to Spain with one tapping in France, and then they will expand it. Maybe, I don't know how it will happen in the future, but it will not be all the lines in one position, and it will not be any of the 20 proposals that are now out there, because it will be something that grows, and yeah, we'll see how it happens. So I hope this is a answer to the question.
Okay, thank you very much. Very well. So, Anka Diana submits a comment, which is how ministers from 9 EU countries have signed up to a plan to develop an integrated offshore grid in the North and Irish Seas. The agreement was signed at the Energy Council on December 7th by ministers from Britain, Belgium, Denmark, France, Germany, Ireland, Luxembourg, Netherlands, and Sweden. The North Seas countries' offshore grid initiative calls for improved multilateral
This is also
collaboration.
something.
It also recognizes the need for a
Yeah, this is something that
coordination supported
what I
by
would like to add
experts.
here is that
So thank you for
indeed it's
this
ministers that say
information,
that we need to have
very
this
important.
super
So
grid,
I don't
and
know
they
whether.
might not be the most. I mean,
Go ahead.
yes, this offshore grid is something that I think is very challenging, but it may not be ready at this moment, and we have to see whether this is at this moment a good idea to put it right there. There are still some developments needed, and as I mentioned, I experience a lot of positive feedback from people who are not really into the technical part of the discussion. That the people from Greenpeace that really like to have this supergrid, and it's a good idea. Let's see how far that and how fast that we will get there. So I'm quite hesitant. I'm in favor of a supergrid, but I think there is still a lot of work for researchers to be done.
Okay, very well. So just to complete this information, this person indicates that the elaboration of the first leg of supergrid between UK, Germany, and Norway was signed today in London with an estimated cost of 34 billion euros. So we hope that this is a real kickoff of the first supergrid in north of Europe. Great. So